In this video, we're going to look at the different addition reaction mechanisms that we've talked about thus far in Unit 5, and we're going to have a specific focus on the stereochemistry of the products that are produced. If you continue on in organic chemistry, stereochemistry is very, very important because one compound may react one way where its enantiomer or its diastereomer may react a completely different way. And so stereochemistry, very important. And what I want to focus on is why the stereochemistry for a lot of these makes sense. So we've talked about with SN2 reactions, how if we had something that was like this, we had sodium hydroxide where our nucleophile can come in and knock out. Because it's coming from the back end, there's an inversion of stereochemistry that we get with SN2 reactions. Where on the flip side, let's say we had this same situation, except we had an SN1 reaction. So let's just say sodium hydroxide again, since that's a tertiary carbon, definitely leaving group has to leave, and so leaving group leaves, and when it does that, we get an sp2 hybridized carbon, which is trigonal planar, and now our nucleophile can come in and attack the positive charge, and because it doesn't have to kick out a nucleophile, or excuse me, a leaving group, because the leaving group has already left, we are going to get a wedge OH, a dash methyl, plus a wedge methyl and a dash OH. And that's because at some point we had a trigonal planar carbon, and so it was flat, and so our attacking group, our nucleophile, can attack from both the forward and the reverse directions. There's no steric hindrance there. Now that doesn't mean that we're going to necessarily get 50-50% as far as our reaction mixture, but we're not going to get 99-1 either, okay? So let's look at some of these. We have the addition of HBr, and when we add HBr, what happens first is our nucleophile, the double bond, attacks a hydrogen. And what we do is we are going to create a carbocation that puts a positive charge on the most substituted carbon, and then our bromine can come in and attack the positive charge. Let me change this to this structure, because what we're going to see is we're going to get, because it was flat at one point, we are going to get a wedge methyl and a dash bromine plus a wedge bromine and a dash methyl. Okay, so what you need to know for this type of reaction is rearrangement can happen. That it would be a methyl shift or a hydride shift. Those happen oftentimes. Not here because we were already on a tertiary and there was no way to make it better. And if a new chiral center is formed, you will get enantiomers or diastereomers, and we'll talk about when you get one over the other. It just depends on if there's stereochemistry. So for example, let me finish writing this and then I'll show you. Let's say somewhere down the line, and I'm just drawing a wedge. Well, if that's not part of the reaction, then that wedge is going to end up in the products. And so these guys, because not everything changes, they are technically not enantiomers. They would technically be diastereomers. Okay, and so this is called Markovnikov addition. Remember, Markovnikov means that we're going to add our group to the most substituted carbon, and the reason why we do this reaction is to add that bromine. Okay, now we have acid catalyzed hydration of water, and with that reaction, this is just sulfuric acid, commonly dilute sulfuric acid, just dissolved in water, and so what we're going to get is H3O plus. That's going to really be our reagent. And so just like the first reaction, Markovnikov addition of HBr, we're going to take a hydrogen, and we're going to put that on the most substituted carbon within the double bond, so that'll be the tertiary one. We're already tertiary, so we don't need to worry about rearrangement, but understand this is the other one that we're going to go over that can have rearrangement. And because we go flat at one point, when water comes back in and the oxygen nucleophile attacks, it's going to be able to attack from the forward and the back direction, and this is catalyzed, and we'll see why this is catalyzed, because another water molecule will come back in, take off an H, and give it back to the oxygen. And so what we get is we're going to get, and we can say plus enantiomer, that's very common, but here I'm just going to draw the other product. We're going to get both stereochemistries. Okay, so we expect a racemic mixture where we get both enantiomers. Okay, and this makes sense why we get both, because at one point it went flat. Okay. Here in this example, which I'm not going to do, I guess I'll do it quickly, because I feel like at this point we've covered this. We are going to get a positive on a secondary, so we'll have a hydride shift, and that is why that alcohol group ends up forming there. And one thing that's important is this is not a chiral carbon, because we have methyl and methyl, and so that's why you don't see any stereochemistry in the products. This is a great way, this reagent, H3O plus, which is sulfuric acid dissolved in water, is a great way to add an alcohol group. However, because rearrangement can happen, it's not always going to behave as you might predict, because you really have to think through. And so what we're going to have are other methods. Here we have hydroboration oxidation, and I'm looking for the other one. So before we get for some reason it hasn't showed up here, so I'm going to write this. We have oxymercuration, demercuration, which is mercury acetate dissolved in water, and then sodium borohydride. And this is going to be the Markovnikov addition of an OH group with no rearrangement. And I can show you the mechanism. You do not need to memorize the mechanism. It's a little bit beyond what we're trying to do here, so no need to memorize the mechanism. So it may be a little bit confusing. So mercury acetate is a compound, and I used Mg, but that should really be saying Hg, because that's mercury. That's my bad. So we're going to have Hg bonded to oxygen acetate. And we have two of those. And what actually happens is this nucleophile attacks the mercury, because remember, mercury as a transition metal, if it has two acetates here, it's going to be positively charged. And so what we get is this, and one of the acetates leaves. And this mercury attacks that positive charge. This is a very strange reaction the first time you see it. And so what we get is this partial bond where this group is still kind of delta positive, still kind of positive, because that bond is very, very weak. It's almost like an intermolecular force, although because it's within a molecule, we can't call it an intermolecular force. Water comes in and attacks that carbon, and that causes that bond to go back to mercury. And then the acetate, which we can say OAC, or we can draw it as this, comes in and is going to remove a hydrogen from our oxygen. And we get this. Now, that was all step one. And then in step two, NaBH4 will remove HgOAC off that molecule. And so, long story short, you don't need to know this mechanism. We are going to get both enantiomers here for our alcohol group. So long story short, we're going to get both enantiomers. Okay, now, hydroboration oxidation is another way to add an alcohol group, except we're going to add it at the anti-Markovnikov site, or the least substituted, and we're going to get syn addition with respect to the H group and the OH group that we add. So, what does that mean? That means we're going to add an H and the OH, and they are going to be the same stereochemistry. Syn means same. And so what you want to know is we're going to get enantiomer, so wedge OH and dash OH, but what matters is that you also consider the H that was added on the most substituted carbon as well. Okay, so if we predict the products for these reactions, we are going to add this to the least substituted carbon. We're going to add an OH group, and so we're going to get boom, 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 and we're going to get OH, and let's just say it was a chiral carbon where the OH was added, although it's not. We're going to get OH, and then an H plus a dash OH, and a dash H. Okay. Here might be a great example of one where it will matter. You will get wedge methyl and dash OH, wedge OH and dash methyl. And if you were asked the hydrogen that was added at the, and I just added that to the most substituted, and I needed to add that to the least substituted, so I'm going to fix that really quickly and it'll be just fine. H, OH, H, OH. So those would be the two products that we would get, because this adds to the least substituted carbon. A good way to know that you're adding like whatever group that is the main focus of your addition is if you have a peroxide, almost always you're adding it to the least substituted. And so here, this is a great example how you don't always want to be thinking of enantiomers, although you are forming kind of enantiomers. Here's why. we are going to add a OH group to the least substituted, and I'll just make it a wedge. And then here we must have a wedge H group because it's syn addition, leaving this to be dashed methyl. But what is also going on is this guy is never reacting. It's not part of the carbon that's on the double bond, so it's not reacting. So when you think you're drawing the enantiomer, dash OH dash H, which you don't have to draw on the H's as long as you have a wedge methyl on this carbon. This guy is still going to be a wedge, that top carbon, so these are really diastereomers. Okay, so if you want to go through and do this on your own, the 3 ways to add water. The first one here, we could have potentially rearrangement. The second one, no rearrangement, but we're going to add our water to the most substituted. Here, no arrangement as well, but we're going to add our water to the least substituted. Now, we're going to do halogenation, which we could have Br2, we could have Cl2, or we could have I2. Those are the ones that we could have. And we are going to add a diatomic halogen across a double bond, and it's going to be anti-addition. And here's why. This makes a lot of sense, hopefully. We're going to attack a bromine, and here, let's add a methyl group just because that way we know that we're going to add the first bromine to the least substituted. That way we have the most substituted carbocation. And then Br minus will come back in and attack the positive charge. But like we've talked about previously in this video, this is flat. So whatever stereochemistry that bromine adds, it doesn't really matter because this is flat. So the second bromine is going to add from both sides. Additionally, this was a flat carbon as well. This was sp2 and this was flat. So what you're going to get is both combination, wedges and dashes. So this, if I fixed it, adding that methyl, we would have dash methyl here, wedge methyl here. Okay, anti-addition. Again, when things go flat, we expect our nucleophiles to be able to attack from both sides. Same thing here is we could have bromine dissolved in water. We obviously add the halogen to the least substituted, and then we'll add an alcohol group if it's water, or we could have something like ethanol. And if this were ethanol, how would this change? I'll show you really quickly. The H would go away, and we'd simply just have an ether group. So the O would be there, and it would tack along with it however many carbons there were, okay? Again, in this mechanism, we're going to get a bromine added, and then we have a flat carbocation intermediate here. And so because this is flat, our water or our alcohol group can attack from either side. Okay, one other one that I wanted to put, which I guess I didn't put in here, but I'm going to put in the notes because it's one that we talked about, and it's catalytic hydrogenation. And this is, let's just say we have a double bond like this. And this is where we just get rid of the double bond by adding a hydrogen across the double bond. And of course, we have to have a catalyst present. What's going to happen is we're going to have syn addition of our hydrogens here. So here we have the stereochemistry goes away, but really what we have is we'll have H and H, which means this guy's got to be a dash, plus it's enantiomer, so enantiomers will form. Okay, we're not going to go over the mechanism. We have to know free radicals to be able to do this mechanism, which you will learn if you take organic chemistry in college. But for us here right now, we do not know free radical mechanisms.